We're going to start talking about some of the common structured data formats that are encountered in biomedical sciences and what some of the different Python tools that are available to work with these particular kinds of data. Oops. So I would say that structured data is one of the most important computing concepts in biomedical sciences. The structure allows data to be stored, shared, and recalled in a manner that reduces ambiguity with regards to the nature of the data. So I've put up here some links to some resources. So here's a discussion of open data formats and particular Python tools that can handle them. And here's a link to the Open Data Handbook that these examples are drawn from. So in reality, we've already experienced several forms of structured data. So a comma separated value file or a tab separated value files are in reality a form of structured data where we know that values are separated by known delimiters. If we add a header row to that file, then we have the known delimiters and names to be associated with the different values. We have done things with images so far, so we've played around with DICOM images, regular photographs. So the DICOM image is a specialized digital image where the header provides in a structured format information about the patients, providers, imaging procedure, etc., in addition to the nature of the pixel data, the size, shape, representation, etc. EXIF is the header, is the standard way to store header information in photographs, and it provides information about how the image was captured, for example, what the camera settings were. Images themselves are defined with several structured formats such as TIFF, JPEG, PNG, etc. And these are all structured forms that tell us how the pixel arrays are, how large they are, what the shape is, how many bits per pixel, etc. We've messed around with FOSTA files, which is a simple description of sequencing. And there's a more informative format, FASTQ, which has information about the quality of the measurements made for each element of the sequence. So there are several structured data formats that are of particular importance, and we're going to go over those. So HTML, XML we'll talk about in the next class. And so today we're going to go over RDF, Resource Description Framework, JSON, JavaScript Object Notation, DICOM, which stands for Digital Image Communication, and HL7, which is Health Level 7, which is this standard format for messaging within healthcare. So RDF is a standard model for data interchange on the web. And this is taken from it's a W3 standard. RDF has features that facilitate data merging, even if the underlying schemas differ, and it specifically supports the evolution of schemas over time without requiring all the data consumers to be changed. So RDF extends the linking structure of the web to use URIs, stating the relationship between things as well as the two ends of the link, blah, blah, blah. So you can read these, and I think where RDF has really become important in biomedical sciences is that it's become the de facto standard for representing knowledge. So, and what it's generally structured into are graphs where you have nodes and edges, and the edges represent relationship between concepts, or here they're using arcs. And the standard Python package for working with RDF is called RDFlib. And here's a link to some example resources where RDF would be useful. I have to say that I am in no way an RDF expert, and I've been trying to learn it because I'm collaborating with people that are using RDF for knowledge representation, but I am basically just showing this to you as this will be an example of declarative knowledge. There's not a lot of procedural knowledge that I have with RDF. So we can install RDF-lib with pip, and having done that, let's look at the structure. So an RDF graph is a set of RDF triples. So that's kind of the main thought, that this data is stored in triples. And here I've just pulled some examples from the RDF-lib tutorial and other kind of web resources where I'm importing the package. I'm creating a RDF graph that's going to store my data. And then I'm parsing a file, and I have, this is just there's various different file formats that RDF can be stored in. This is the NT format. And so I'm parsing the contents of that file and reading it into the graph. And when we're done parsing, we see that there's two elements in the graph, 2 nodes. And then I can print each statement, and you can see that each statement consists of a triple. So here we have RDF-lib term URI reference, this is a big asterisk, etc. And then we have that it's a type, and then we have a person, and here we have a statement that example.com says, hello world. So one of the standard, well, I guess I'm not there yet. So there's different kind of tools that can be imported from RDF-lib. This B node creates a unique identifier to use for the node. So here we're creating a concept for Bob, and we're assigning to him the URI reference example.org people Bob, and then we're creating another person, Linda. And so we're creating a name, which is an RDF literal of Bob. We're creating an age, which is another literal with the value 24. And then a height with the literal, or we're using a float. So now, if we want to add concepts to the graph, we can use the add method. And you see here, we're adding these triples. We're adding to Bob that he is of type person. And then we're adding this friend of a friend. These are different RDF definitions. So this has a concept of what a name is. And then we're adding the value of Bob of name. And then we have a concept that knows. So Bob knows Linda. And then we're adding Linda to the graph. And this is a type of a person. And then to Linda, we're adding the concept of a name. And then we are serializing this out, and then this is how that data is printed out. So this is a bunch of prefix. These are kind of shortcuts or abbreviations that will be used in the rest of the file. So we have ns1 is pointing to this xmlns.com FOF 0.1, and that's where our definition of a person. So you can see that we've defined this prefix ns1, which is standing for this concept that would be attached to person. So that's telling us when we have a person, what do we mean? Well, we mean what's defined up here. Here's some more examples. We're creating a graph. Again, we're creating a unique identifying node for Donna. We're adding characteristics of Donna. It's a person. Um, I don't know if Nick is a nickname. We have a name, which we're using the literal Donna. It has a concept of a mailbox. And so then we're adding what the mail address is. And then we can iterate over the triples in the store. So we have the subject, predicate, object. Again, so we're iterating over all these triples, and we're doing tuple unpacking of the triples. And then we can print them. And then we can grab all the mailboxes for a person and print the mailboxes. And see here we're printing over the triples. And here we are printing the mailbox, which is Donna at example.org. Okay, one of the standard examples is this Berners-Lee card at the w3.org website. So we can, the previous examples we were reading things from a file. Here we're parsing just a web resource. So I haven't downloaded this. I'm just going to be accessing it via the web, parsing it, and putting values into the graph. So when we're done, we can see that this has been, the card's been updated since the example was generated, that the graph has 87 statements in it. And then we can, again, we can iterate through the triples, the subject, predicate, objects, and we can check to make sure that there's no broken structure in the graph, and then we can serialize it into a different format. So this time we're using an N3. Previously we used the turtle. So this is the content of that graph. Here are our prefixes, our abbreviations that will be used in our triples to kind of compress our code. Okay, oops, looks like I was missing. Let's see. Oh. So I can prepare this RDF. I'll mention this in a second. It has its own query language called Sparkle. So here I'm generating a Sparkle query, and I'm going to be asking questions about it. But I didn't get any output from this query. So here I'm defining some prefixes that will be used as shortcuts in my query. And so I'm going to take the graph that I've created from the w3.org website example. I'm going to select names, and then in my query I provide these matching triples. And when I do this, I have pulled out one person, and so I'm just printing the row here. What was pulled out was the term literal Timothy Berners-Lee. Okay, I mentioned that where this really comes up within biomedical sciences is knowledge representation. And there's various formats for knowledge representation and ontologies. Here's an OBO format, and this is what is being processed in the current homework assignment. And this is the same disease, now instead of the OBO format, represented in AL format, which is RDF. And so with those examples, then we can parse the data file and create this RDF graph. And you can see in this case our disease ontology. This is the human disease ontology. There are roughly 188,000 nodes or concepts in that ontology. And here's a cell line ontology. Just some different ontologies if you're interested in playing around with it. This one has 270,000 nodes or concepts in it. And we can do, in addition to querying, adding, and deleting objects from individual RDF graphs, is that they have set-like operations like union, so I can add two graphs together and get a new graph that has 458,000 nodes or concepts in it. Okay, since we looked at ontologies and I showed you what an example OBO format is, we can also, OBO itself is a structured data format, and like I mentioned, the homework assignment for this week is to read in an OBO file and structure it into the data into some classes. And I just did a simple web search and found an OBO parser for Python, which I've downloaded, and I can use this to parse the OBO file. And let's see. And I created this. This returns a generator, which is a Python object that returns one element of a sequence at a time. And so I can sequence through here and look at, so here we have the concept of angiosarcoma, and we have its identifier, alternative identifiers, etc. Here's Laren Hugh, that's who created it. We have pterygium, whatever that is, but it is a kind of a corneal disease. And that's what, in the homework, you're reading in this concept, and then you have this ISA. It points to its parent class, and this is a way that we can navigate the graph. So this ISA in a graph representation is going to be an arc or an edge between nodes. And in the homework assignment, it's going to be a link via that you're referencing the key in the dictionary. Okay, health level 7 is the standard for messaging in healthcare. There's health level 7 version 2.x, and that's what we're going to be dealing with. And I think that's still what is standard usage. There is a HL7 version 3, which is XML based. But this is a structured data format that looks like just complete gibberish to me. But this is how information is exchanged in healthcare currently. So we have like an admit, discharge, transfer message. And so we have like event identifiers, we have a person, we have an address, and so on. So there's a couple of different Python libraries for working with this. There's Python HL7 and HL7 API. The HL7 API seems more advanced in that it lets you generate messages in addition to just reading them. And so again, this can be installed with pip. And we can create messages. So here I'm creating an admit, discharge, transfer message, and I am adding fields to it. And in my mind, these are just gibberish, not very explanatory. And then after we've created the message, we can try to validate it and ask, have we created a valid HL7 message? And in this case, we have not. Here I'm creating a string with the messages, and I'm concatenating them together and parsing it and asking now, is this a valid HL7 message? And it is. Okay, JSON is just a standard computer serialization that's much simpler than XML or RDF, and so is becoming very common. for applications where people don't want all the redundancy of these other methods. And from a Python user point of view, JSON is part of, there's a JSON library that's part of the standard Python distribution. And from the user, it ends up looking just like a dictionary. JSON is actually the format that the IPython notebook is stored in. And so that's how in the NB stripper application, we're using the JSON package to read in the library, the notebook. So here's just some different data that's been stored in different applications that I've used, and it's been serialized to disk, and I'm using JSON to read it in. In this case, I'm just reading in. This is what it looks like on disk. So this is just the ASCII file itself. And then I can read it in with JSON, and you see we have this dictionary structure with the keys and the values corresponding to the different concepts that were laid out in the file. And then I can dump data out, and I can read it back in. Okay, so image files, we can use various tools in Python to read the pixel data, such as the Python imaging library or packages, sub-packages within the SciPy package. But if we want to get the EXIF information, the metadata about the image, we need to have a different library. And so one that's available in Python is exifread, which allows us to extract the EXIF tags from JPEG and TIFF images. So again, this can be installed with pip. And I've put up a photograph, just a panoramic photograph from my iPhone. And this is all the data, metadata, structured data that is stored in that photograph. And so we have like these key value pairs. So I have an aperture value. Let's see what gets down here to anything interesting. So this is the date that it was taken. What the color representation that was used. Which XF version this is being stored in. What the focal length in 35 millimeter equivalent it was. What my location was in longitude, etc. So one thing to be aware of is these photographs, and if you're thinking about yourself and privacy, there's a lot of information that's likely stored in the photograph. From a health research perspective, you can think about photographs having a lot of PHI information that would be not HIPAA compliant to be stored in a de-identified file, such as the date the photograph was taken. And here, so I'm using the EXIF package to read the header information, and I'm using SciPy to read in the actual pixel data. And that's from Antelope Island. Okay, so DICOM images. So DICOM stands for Digital Imaging and Communication in Medicine, and it's a standard for storing and communicating image data. And it has a lot of metadata about the image acquisition, patient demographics, interpretation, etc. And this is stored in the structured header format where you have a tag element where you have a tuple, a two-tuple of a group number and an element number. And if you've had the biomedical informatics standards class, you know that this is not a respected format because these elements have semantic meaning. So these different groups have particular meaning. So you'll have patient demographic meaning, you'll have physician groups, you'll have procedure groups, and what can happen there is you run out of numbers that you can use as details proliferate. So, and then there's also the pixel data, and the header will tell you how many bytes do you have per pixel, etc. So PyDICOM is a pure Python module for working with DICOM images that we've already played around with some, so we can read tags, we can modify tags, we can access the pixel data, and then we can modify the pixel data, and we can read and write the images back. So if that has not already been installed, we can do that like so, and we can read in a particular DICOM file, and we can. There's various tools for, because the header the dictionary that describes the header is fairly complex. There's tools for letting me query, well, what are the fields that include the string num in it? And so here we see that there's a session number, there's acquisition number, there's instance number, there's series number. And so I can access a particular field acquisition number, and it has a value of 1. And if I just print the whole DICOM file, then this is printing out all the fields that PyDICOM knows about. And I can access particular fields not by their name, but by their group and element hexadecimal values. In this case, I'm accessing the patient ID. And you see that we have our group and element number, the name, and then this is information about the nature. This is a long integer, and that's the value that's stored with it. And then we can show the data the pixel data that's been read in.